We got a full docket today, so I'm gonna try to go real quick and get started. So let's do introductions really quick first. I'm John Luft with GSLEP.
Bonnie Baxter, Great Salt Lake Institute, Westminster University.
Thomas Bosters with Brownshire Cooperative.
Angela Gone, Forestry Garden State Runs.
Christine Rumsey, U.S. Geological Survey.
Gary Belofsky, University of Notre Dame.
Kyle Stone, Great Salt Lake. Disclaimer, meeting is being recorded.
Good.
John Leo, Great Salt Lake Ecosystem Program.
Jessica Bowman, Great Salt Lake Ecosystem Program.
You got to get used to that. Jessa's new, so she's not sure where she is yet.
I say she slept.
There you go.
Carter Page, GSLEP.
Remington Austin, Pheasants Forever.
And I'm going U.S. Geological Survey. Listen, yes. Laura Vernon, Water Resources.
Tom Arnold, Water Resource. Henry Davis.
Olivia Preston, Great Salt Lake Institute.
Anna Meyer, University of Utah. George Gregory, Great Salt Lake Institute, West History University.
Jim Van Loon, Great Salt Lake Ecosystem Program. Paul Astor, USGS retired. And then I'm Connor Simon, also with GSLEP. And then I'm going to read off who we have in the chat. We have James Harris, Linda Freitas, Paul Thompson, Rob Dubuque, and Zach Nelson.
Awesome. All right. I think there's a couple more folks going to show up here, but we'll go ahead and get started. And the first thing I was going to give a brief history and then kind of a couple of announcements, but history of our program, like 10 or a little over a decade ago, we assimilated the waterfowl folks into GSLEP. With that, and primarily that was because they were under wildlife and being supervised by those that have to deal with big game. So essentially the waterfowl folks got ignored because big game is kind of a pretty warm turd. So a lot of times people have to focus on that. So the waterfowl guys needed a little bit of cooperation, support, and that was why they put them in with GSLEP. So that added a little bit more to our program. Those guys have been doing the same, working under the same budget since probably the early 1900s. I don't even know, but they have continued. In that time, we've had a few people retire. Those jobs were never replaced. You probably remember and Clay. Those jobs got replaced. There was waterfowl managers that never got replaced. So in that time, there's just been this accumulation of more duties for both the waterfowl crew and for GSLEP. Obviously, over the last few years, we've had a focus on Great Salt Lake because of water levels and whatnot. So everybody's kind of had more lumped onto them. But and you know, with the waterfowl crew, there's been we're dealing with a lot of infrastructure that is, you know, almost 100 years old when it was put in, and some of that stuff is starting to decay, and we're trying to get some of the money and grants to, you know, make them safe again. We've actually had bridges, people on them. There's, I don't know, dealing with graffiti, these WMAs, cats and dogs living together. It's chaos for the most part on some of these places. So what has happened more recently with some of the added WMAs like Bear River Bay and Willard Spur and the Black Hawk and more properties that we have to manage, we did get probably several months ago, or I can't remember how many months ago, but there was an announcement that we were going to hire for a new Great Salt Lake Ecosystem Program Manager. And incidentally, most people, when that job came out, were saying, "Isn't that your job?" When I was like, "It is kind of my job." However, that was the way that we were going to start adding new folks onto the program. Kyle was selected for that job, and so in that time frame, so between now and then, we really kind of have been operating under the same structure because Kyle was already the biologist on the program. And so when he took that position, we needed to fill the biologist, which is now been filled by Jessa. And so we're essentially fully staffed. But what I wanted to announce today is from moving forward, Kyle's going to be the point of contact for GSLEP. Doesn't have to be me, and I thought I'd make that here to save a lot of email back and somebody sends me something and then I say, why don't you work through Kyle on that? Instead, from now on, your contact will be Kyle. So like, for example, the Salinity Advisory Committee, Kyle's going to be the one that takes over for that. And I'm kind of, I know Thomas is semi-retired. I'm not semi-retired. I can't go anywhere and I'm going to still be here, but we need to redistribute some of the work and try to make it alleviate some of the issues, me not responding to people or whatever it is. So this is going to make it a little bit easier. I think if you ever go to like a mechanic and the mechanic goes, "Hey, this belt is looking worn, sprays in it and stuff, you might want to change that out." And then you don't change it, and then it breaks, and then you can't do anything.
Wait, are you the frayed belt?
Yes, I am actually equating myself to this worn, frayed, messed up. It probably should be replaced. So how does the belt
I thought John had a mechanical project. What?
yeah.
So are they recycling the old belts somewhere?
The old belts get tossed up on a heap and somebody goes, "Hey, if we ever find another car, we might be able to put that one in." So anyway, this is kind of a new or a quick fix for us to move forward and kind of a way to announce that Kyle will be the one that takes over. And if you've got calls, questions, or new assignments with new committees or new things that has anything to do with the Great Salt Lake, Kyle's gonna be the guy. So moving forward, we're gonna do that starting now. So,
And my email just cracked.
So if I have salty memes that I usually send you and now.
yeah, now it's Kyle.
Yeah, it's almost.
And what are you gonna do, John?
He's gonna manage the
What are you going
program.
to do, Broken Bell?
So I'm gonna sit in there and
Do you guys get him a recliner?
stop trying to pull my hair out. Kyle's already ahead of
Rocking
me.
chair.
Yeah. So I've been just like running ragged and want to just go nuts all the time, pulling my hair out. Kyle is already ahead
Sorry,
by
his hair.
not having to
Yeah.
pull his hair out. So we're set. So yeah. So I just wanted to let everybody know. So Jeff and Angela and Tom, anybody that has anything that they want to, start or ask or go through GSLEP, it'll be Kyle moving forward. Now, after that, there's been a few folks come in, so I'll let you guys introduce yourselves, get caught up.
I'm Lauren Head, PhD student at Utah State University.
And Brian McCarthy-Zach, MS student at Utah State.
And who else?
Guy Briner,
yes.
just an interested participant.
Jess.
And it's a long ways out here.
So Bill Brown, Brighton Cooperative.
Mike Conover, professor at Utah State University.
Okay, and I think that's it. And then one other announcement that I wanted to make before we get started is there's the Association of Field Ornithologists and the Western Bird Banding Network that is going to be holding an event this summer, which is between July 29th and August 1st. That's the website. I think you have to register for that, but I just wanted to let folks know that might be interested in some bird activities towards the end of the summer, that's available.
And where is it going to be?
It's going to be at Weber State. Yeah, I believe that's correct. So, all right. Let Connor get us kicked off here.
All right, so again, I'm Connor Simon, I'm a biologist with GSLEP. And what we're gonna start with today is going over the brine shrimp. So we're going over some brine shrimp demographics. We're gonna kind of go quicker through some of the more demographic information. A little bit of meat of this is gonna be about the model. So we're gonna be predicting what we're gonna be seeing next fall in terms of cis counts. So some of you are familiar with these figures. I'm still gonna go over them again so we're all on the same page. So most of these demographic figures are all gonna have the same structure. So on the y-axis, we're gonna be looking at whatever parameter we're particularly focusing on in the figure. X-axis is gonna be month. And then on the left hand, you're gonna have summary statistics from each month. And then we have a legend here. And this kind of just describes what different lines we have going on the figure. The thin dotted line are the maximum and minimum values observed for whatever parameter we're looking at since we started collecting data. The grayed out regions, which are kind of a little bit faded on here, you can kind of see them bordering either side of the kind of denser sectional lines. That's the 25th and 75th percentiles. The dark black line is the running average for 1994. The thicker dotted line is the 5-year average. The gold or yellow line is the previous year's data. And then the red line is the current year's data. So for this figure, we're looking at temperature. So if we look back into December of the previous year, start of winter, we were right on average. It was dropping. And then we had an interesting January. It was a little warmer than usual. We were actually above the 75th percentile. As we crossed into February, that dropped below the 25th percentile. So we kind of went inverse there. And then right around now, going into the spring, we are about average. So right around the historical averages in terms of temperature. Sometime in February, we did cross that approximate 40-degree threshold for shrimp survival. So it's looking good right now in terms of temperature. Now moving on to salinity. So as we go into the spring, we actually are following a very similar trend as last year. We're low. Salinity is low right now. We're riding right above, a little bit over 10% salinity. And something to focus on with this figure, it's salinity is represented as a percent on the y-axis, and this is specifically surface salinity. So we're focusing on the freshwater lens here, taken with the refractometer. This does not represent the entire water column. Again, so we're actually below the 25th percentile right now. Salinity is low, and with all of this precip we're getting, even today we got a bunch of snow up here. We're expecting this is probably going to go down a little bit, and we're just going to have to keep an eye on this moving forward. But we are following the same trend as last year. All right, so now we're looking at chlorophyll and micrograms per liter. We actually kind of have a funky story going on here. We're not entirely sure what's going on, but so going into December, shrimp are dying, it's getting cold. As we would expect, we start to see a bloom, right? So it's colder temperatures, the chlorophyll is, the phytoplankton out there are happy, and they start to bloom. Now, as we move into January, this actually flipped. They started to drop unexpectedly. And this kind of persisted through the winter. We were below the 25th percentile. Now, this is odd. And right now, we're right around average with, not average, but we are right around where we were last year. But we also have not the eye hatching. We'll get to that in a little bit. But with Nambion hatching, we've got a lot of grazing pressure right now. That's probably still going to go down. Now we're really going to be relying on this freshwater input coming from the mountains, bringing nutrients, and hopefully allowing the phytoplankton to rebound. But this is a little bit different. Now we think it might be due to nutrients. That could be microbialites sucking up nutrients, maybe a little bit of flushing to the north line. We're not entirely sure. But this was a very odd winter for the chlorophyll levels in the lake. All right, so now we're looking at cyst density going into December. We saw cyst density increasing. Moving through the winter, it started to level off. You have some harvesting. And right now we're riding right around where we were last year, a little bit below historic averages. But we're going to get more into this when we get to the bottom. Now, nuclei density. So this is another kind of a cool story, kind of cool figure to look at. So as we go into the winter, we do not have any hatching. The system dormant, which is what we would expect. We move into February and March. We start to see some hatching take place. And this year, our peak actually took place earlier than last year and earlier than historic averages. And we set a new maximum for this specifically for the month of March. Last year, the nuclei started to hatch a little bit earlier. You can kind of see with this golden yellow line increasing before the red, but we can see that those intersected and are hatched very rapidly. And that is going to have implications for the chlorophyll levels and the grazing of phytoplankton in the lake, like we just talked about. And moving on to juveniles. Now that red line might look like 0, but it's not. Now it's actually at about 0.05 on average for March. And this indicates that the nuclei are advancing past that bottleneck. They are going towards adulthood. They are moving through their life stages. And our shrimp population in the lake is starved. So these next couple of figures I'm going to go through pretty quickly because it's all about adults. And only any adults in the lake. It's going to be the same story for all of them. So this first figure is males. We didn't have any in the lake. They kind of persisted into the early winter, died off sometime around January, February. Same story for females. Some persisting into early winter, dying off in winter. We haven't seen any yet. Females with eggs, females with cysts, and total adults. Again, we had some adults persisting into early winter. Temperatures drop below the threshold of survival. They died out, and we haven't seen any adults yet. Since we are starting to see juveniles, we might start picking up some very young adults soon, but we'll have to see what happens in their next year. All right, so this is a newer figure. I want to reiterate for anyone that hasn't seen this before, it's kind of a unique figure that we just added, I think, last tag meeting. So this depicts brine fly larvae. Now, this is a very unique set of data. So when we go on our shrimp runs, we're taking a vertical tow using a plankton net. That's how we collect our cysts, how we collect our shrimp. And we end up getting sometimes bycatch. So we get fly larvae bycatch, and we do enumerate those. We've been doing that for several years. So we do have a fairly large set of data to work with. So on the y-axis, what this represents is the density of fly larvae per meter cubed in the water column specifically. So this doesn't necessarily represent what is happening on the microbialites. It's exclusively what's happening in the water column. And this is one piece of the puzzle of brine flies that we're all trying to figure out in the lake. Where this fits into that puzzle, we're not sure yet. But we want to express that we have information and we're sharing it, and it's something to work with. So going into the winter, we caught some flies in our samples that leveled out as we moved through winter. We had a little spike in February, still relatively low, which is what we would expect. We think the flies are dormant in winter times, colder temperatures. And as temperatures warm in the summer, we expect that to increase, but we're going to have to see where that goes. Again, this is tentative data. We're just starting to work with this and play around and see what it really means. But it's cool data, and we're interested to share. All right, now we'll get into some more of the meat of the presentation. So we're going to be going over the harvest model predictions. So this looks complicated. We're going to break it down real quick. So for those that aren't familiar, what we do is we take the information in terms of cyst counts that we collect in the spring, and we use this information based on some models that Gary has worked on over many years. And this information is then fed into those models, and it kicks out some expected cyst predictions, essentially, for the coming fall. It helps us understand how many cysts we're going to be seeing in the lake. Now, what this model is comprised of is two piecewise regressions. And so essentially the density independent side is the left side of the model that you can see from your perspective. And the density dependent side is the right side. And those each have different regression equations. We basically take our spring sys counts, we plug them into the equation, then it gives us the expected or predicted values. So in terms of our current spring data, we could only use January and February data. March, we started to see nuclei, which kind of renders this ineffective. And then in December, we still had some adults persistent. So what we saw is the spring sys counts range from 18.7 to 41.33 sys per liter. This essentially puts us on the x-axis. You can see the spring sys per liter. Y-axis is our predicted fall sys. That red circle indicates where we are at on the model. So we're on either density independent, density dependent side. And we essentially have an overall prediction of about 121 sys per liter. Now this slide right here includes all of our data. No outliers are removed or anything. Now, given that we go sampling sporadically, opportunistically, sometimes we'll catch streaks, super dense sites. Now this slide here is when we remove those outliers. Kind of improves our confidence. And it drops the, it was about 40 something sys per liter down to about 35.5 sys per liter. Now this also tightens up our circle that you can see on the top of the model. We move up towards the peak a little bit. And now we are sitting at about 142-ish sys per liter expected. So we are poised for good sys production this coming fall. Now that being said, hopefully, we've got chlorophyll salinity. There's a lot of factors that can influence this, but we're in a good position right now. And again, this is without outliers or with outliers removed. Yeah, and that's about it. I think that's all I've got. Any questions? Yeah.
I'm just concerned that you dropped the March value because there was hatching. Were there enough nuclei to have made a difference in the sys count?
26 per liter.
It got, yeah.
It
was pretty crazy.
That's why I wanted to clarify
Yeah,
that.
no, so
I've seen the data. I mean, I
Yes.
know that, but I wanted to clarify that it wasn't a small number because the sys number went way down.
It drops.
The system was cut in half.
Right.
So that's why we kept the February data. But we ran it both ways and it didn't change it.
Okay.
If anything, it made it better.
When you take out the outliers, you rebuild the model with data where the outliers have been removed, or you base it on the model that included the outliers?
I believe it's the same model. And essentially, you're just feeding in data.
Okay.
Because I think the model is based on all data, correct? The data that doesn't have.
So part of the model, what it identifies is any data 2 standard deviations above the mean gets treated as an outlier. And that's why we do both. If you remember 2013, 14, when we still had a fairly persistent brine layer, we were seeing those discrepancies because we sampled through the brine layer and we were getting streaks along the brine layer. And we were thinking that maybe they weren't available to the system, but they were in our counts. And it was one of those things where Gary adopted this 2 model stage to just tighten some things.
Yeah, no, and I understand that, and I remember why we were doing that. Maybe it's just me, but if you're going to eliminate outliers and use a model, then you need to, in my mind, use a model that didn't include outliers. The model should be based on data that did not include outliers. This is just my logic. Maybe I'm wrong.
The model had excluded a number of the sys counts that were way out of line in the past. I mean, there were some sys counts that I was given that were through the roof, and you're going, this can't be realistic.
Yeah.
So those were excluded from building the model.
Okay.
right, I think Christine.
Yep.
Yeah.
Cool. Morning, everybody. I'm just Lindsay with GSLEP. And then I will be giving you an update on like. And the lab. So just dive in here. Starting with lake elevation. So here's a plot of South Farm Lake elevation from October 2022 or period start flow through the present. See how it's gradually come up over time as you're all aware. Our most recent measurement as of a couple of days ago of lake elevation was 4193.5. We're up 1.4 feet since our seasonal low last November, where we were at 4192.1. And I've been really curious to see how this year's lake elevations are going to come up, because we started essentially in the fall of the same place we did in the fall of 2023. But relative, so this year right now, relative to last year, on April 1st, or right around there, we were at 4194.3, so we're down about 0.8 feet relative to last year. So we're just really not coming up in the South Arm like we did last year. We look at the North Arm. Again, from October 2022 to present, you can see how our most recent measurement there is around 4192.6. So in the North Arm, we're up 1.2 feet since our seasonal low of 4191.4. And relative to this time last year, the North Arm was at 4190.9. So the North Arm has come up about 1.7 feet since last year. But again, in the South Arm, we're a little bit lower than last year. If we compare the elevations for both arms, like elevations on the y-axis, the South Arm is in blue, the North Arm is in red from October 2023 to the present. You kind of see how we were at a really big elevation difference as a result of the burn being installed, etc. But we started to converge, and those lake elevations kind of tightened up starting last fall, like last summer and last fall. And currently we're sitting at a 0.9 foot elevation difference between the two arms. And now, you know, the following is really synchronous with the continuous flows through the breach. And so we moved to the breach. This is our site, just like 6 miles west of the lakeside breach, and where we have bidirectional flow. This plot is showing discharging cubic feet per second on the y-axis, starting from fall of 2021 to present. The blue circles are south to north flow through the causeway. The red circles are north to south flow causeway. This can make you know it's an open channel and we get flow in both directions. And this green line represents the elevation difference over that period of time between the two arms. And our most recent measurements are hovering around 1,000 or 1,100 cubic feet per second. And I just wanted to kind of highlight that since the berm was raised in February 2023, when it was raised to 4192, we saw, you know, there was an interruption in connectivity between the north and the south. The elevation difference grew between the two arms. I've seen north-south flow as a result since that time. So for I guess, going on 2 years now, until recently. So last summer and fall, we started to see a little bit of discharge coming from north to south. And prior to that, we haven't even seen any evidence of that water. So the last 6 months or so, we're starting to see northbound water trickle back to the south. And because we were not getting any north to south flow, we were able to develop a routing curve for the south to north discharge, which was really helpful as we consider solid nutrient fluxes at this location. That's represented by this blue line. So the discharge, we're showing discharge here from October 2023. Blue line represents when we were able to get instantaneous estimates of discharge at the mid-breach. And then in August 2023 and of 2024, so last summer, we started again to see that north to south flow. We were evaluating the relationship between discharge and elevation. And so since that time, we've been getting monthly field measurements at the breach in both directions. And our last 4 measurements are shown here in January to present, around again 1,000 to 1,100 cubic feet per second for flow going from south to north. And then really low flows from north to south, but we are observing them, and we have water quality profiles that verify that that is in fact warm water, as well as water quality. If we consider lakeside, so that's our breach on the far west side of the railroad causeway, here are discharges for that location. And we are able to measure discharge continuously here. This plot shows discharge from October 2023 to present, so showing last year's runoff pattern, runoff peak, and flows ceased or stopped flowing there last August as well, August of 2024. And since then, the only thing that we're starting to see are flows from actually north to south. So you can see how we're actually getting negative discharges there. And our technicians, we've all observed that there's actually flow from the west, from those kind of canals flowing in from north to south. And it was pretty substantial, getting up into 200 CFS, more recently right around negative 10 or CFS. So it's kind of slowing down, but we are seeing that pattern. And we see that typically in the spring when we get a lot of kind of rain and precipitation in the basin, kind of routing through those canals to the west to drain through lakeside. And I was there like last Monday. The conductivity salinity is very high, so we're at 144,000. So we're really curious about the dynamics in terms of flow as well as the chemistry there, and how drainage from within the basin may be interacting with some of those evaporation ponds out there near the causeway. So this is definitely on our radar, and we're hoping to learn a bit more about what's going on out there.
So that's not all Newfoundland basin water. There's some.
I mean, I think it's unclear, but the salinities were just so.
Yeah.
I wish we could get out to Newfoundland and just actually sample that, so we can get kind of what that looks like, because there is a salt crust out there, so we get precipitation on it. It's going to dissolve cells out there, but yeah, without really knowing more about the starting chemistry of that pool of water, it's hard to know how it might be mixing with these evaporation ponds. The chemistry might tell us something true though, because I would expect the salt dissolving Newfoundland basin, that's Great Salt Lake salts that were, kind of transported out there. If they dissolve, I would assume it might have the same signature as Great Salt Lake. So if we're seeing something different, that might indicate some evaporation quantity. Not sure, but water chemistry might have this too. Okay, moving on to our major surface water inflows. I think most of you are familiar with this, but I'll walk us through it. On the y-axis, we've got cumulative stream flow in millions of acre feet. So this is per location. We're thinking about streams coming into the lake, monitoring the stream flow. This plot starts from the start of last water year. Line is our highest observed cumulative stream flow over the period of record, almost 70 years. The orange line is our lowest observed cumulative stream flow. The green band brackets the 25th, 75th percentile of cumulative stream flow, and then that kind of faint gray line in the middle is our median. And so if we consider Bear River near Corinne, that's our most downstream site on the Bear River, we are just below the median, maybe at 35 to 40 percentile of flow relative to the historic record. And so far, 0.42 million feet of water has passed by the Bear River. If we jump to our site with Weaver River at Plain City, this black line again is where we are this year. It's hovering right around the 25% now, so much lower than our historic record. So 5 million feet have passed by Weaver. The outflow, that's along down the Island Causeway. We are looking a little bit better, a little bit higher than median, and so far we've estimated 1.18 million acre feet have gone by that location. And then finally, Goggin, we're hovering around 70%, so a little bit more flow coming through the Goggin, and we estimate 0.07 million acre feet so far. So as of our just kind of summing up all of those flows, as of a couple of days ago, we estimate that 0.72 million acre feet have come through these inflow gauges. And of course, there are other flows, yeah, there's other inflows that are not kind of captured in this picture. These are the major ones. Relative to last year, this time 0.96 million feet picked on by, so you know, maybe 30% lower than we were last year. And I kind of just like to throw this in here. This is just looking at all these four inflow gauges. The seasonality we are seeing the dare come up as a result of runoff. And telling me that they let a whole bunch of water out of the Pineview Reservoir in anticipation of runoff. So we'll see how the snow melts. We'll see how water use in the basin affects how much water we get. We are continuing to make discrete measurements at reservoir outflow. As many of you know, that's a really complicated site, so it's been very hard to get continuous measurements of discharge here. But we're continuing to make roughly monthly measurements. The last measurement that was made on March 21st, Handy measured roughly 2,200 CFS, so those flows are coming up. And here's a plot of how the discharge, these discrete measurements shown in red, compared to our continuous record at Corinne, which is again upstream of the refuge. I think maybe like 50 miles or so. It's quite a ways. Last year, what is notable is that a divergence between what was measured at the outflow versus what was measured at Corinne. And we kind of all puzzled together that is likely due to flow coming in between Corinne and that outflows into the bay directly, as well as outflows from the Willard Bay Reservoir. This year, we get much more agreement between Corinne and what we're observing at now. And then I wanted to highlight that Andy's put a camera out there. So what's really hard at this site actually in the winter is ice. And so this camera is really helpful for us to just keep an eye on conditions and see when we can go out and make a measurement. So this camera, he's got imagery that's telemetered onto the web, like this was the site page on the web. So that helps us keep an eye on the conditions out there. And then he's also installed surface water velocity sensors out there, both on the east and the west side of the opening. So these data, we're building our way, or working our way toward getting continuous discharge at this location. It's quite an undertaking, but we have really tried to provide the data that are necessary for a model at Utah State University. So we're pairing with them to just try and develop a continuous way, a way to measure continuous discharge like that. That's in progress. And these data are on the web. So if you wanted to see if there are route flows flowing, these water velocities are really helpful for that.
I saw Andy out by the breach one time. So that camera is also available online, the one he had like right at the breach.
Is that fair route flow? Yeah, that should be. I think
That's that one?
this.
Okay.
Not costed, but yeah, these are the one. Yeah.
Okay.
I don't, the new breach, I don't.
That's why, yeah,
Oh,
there,
yeah.
but there was a camera he was like fiddling with that was out there, no?
Yeah, we don't have that for the breach.
Okay,
Is there a weather station out there?
is that what it was?
Other-
Okay, okay. Well, we gave him refuge and beverage. Yeah.
Yeah, it's hard out there.
Yeah.
Okay, and then we'll move on to salinity before Hannah takes a quick look at your chance. So this plot shows salinity in grams per liter along on the y-axis. This is our full historic record from 2010 to present. You can see how we're kind of over here. We're in this happy place of, these colors are hard to see. But we're right around 120 grams per liter. Let me back up. This plot is showing data from our two deep sites. So from Carrington Bay, 2565 site, those points are shown in orange. And then a site in Gilbert Bay, and 3510, and those points are shown in purple. And the shallow salinities are triangles, and the deep salinities are circles. So we're still not observing much of in our sites from the measurements we have. The shallow salinities of these two sites vary from 100 grams per liter, and the deep at depth we're measuring 118 grams per liter. So still not really picking up on any northbound water that might be coming through. And these data are the most recent data are from the end of February. So I threw on a couple of more recent measurements we have at Saltaire. as of March 24th. We measured 108 grams per liter at the new breach. We got a water quality sample on March 19th. And for the south arm, south to north flow, we got 112 grams per liter. And then for our north to south, so the north arm water, we measured 256 grams per liter. And then zooming in a little bit on the salinity record, starting at our historic low lake elevation and the high salinity condition to present. It's really fun to just see how salinity has changed in its trajectory. It's just dropped over time. And then more recently, we're nearing the conditions we saw last year, but not quite. Last year we got down 103 to 100 there, and again now we're 800. More water coming in. I would also expect these to become a little bit more dilute over the coming months. And relative to last fall in Gilbert Bay, we've gone down 8 grams per liter, and then relative in Carrington Bay, we've come down about 10 grams per liter to give you a sense of the season. If there's no questions for me, I'll hand it off to Hannah.
Really, this breach is looking much better.
So here are our from October. We're on track for our GSLEP sites to have everything collected. We are still sending our nutrient samples to the biological lab. We have heard from AWQL that they may have the ammonia instrument ready in about 6 months or so. We'll be watching. As far as our we're doing, we are sending these to AWQL. They've never had, well, that said, they've never had issues with our freshwater nutrients, but there are less issues and they're able to run them in a more timely manner. And we will start collecting more samples at Lakeside as that flow increases. This is our current look of what nutrients look like in the South Arm. I will say that our latest data from Chesapeake is from October, the October state samples. We are starting to get results in from our lab comparison, but we haven't gotten those all in yet. But I would say on average 4 grams per liter, the last total dissolved nitrogen results we got was an NW2O were not quite being right. They're about 3 times as much as they should have been. So we'll have those results also from Chesapeake that we'll be able to compare to the total nitrogen for earlier in the surface and at depth. Here's just a closer look at these dissolved nitrogen and dissolved phosphorus at 2565 and 3510. We can see that everything is converging because we don't have that deep brine layer. And then we're seeing a little more the dissolved phosphorus at 2565 and 3510. You can see how different they are. It looks to be that when we do have the deep brine layer, 3510 is going to get dissolved, not phosphorus at 65. We see when we're looking at where those major sources are coming from. Goggin Bay or Goggin Drain tends to be a big phosphorus source in South Arm. These are the data that we have collected that has direct comparable results between NWQL and Chesapeake Biological Lab. We do see that for our totals, for our phosphorus species, we're seeing Chesapeake be a little bit higher than NWQL. I just took a look at our samples that we sent to High Sierra Water Lab. We have them look at our ammonia and phosphorus species, and I'm going to just, it's gonna look about the same. The difference between what NWQL and about 20% relative percent difference, which we understand that these methods that are being used typically they skew a little higher than phosphorus. So that'll be something to look more at depth in. But we see the same kind of situation at Chesapeake and High Sierra as we compare to NWQL. Our nitrogen speciation is doing pretty well. We do now have ammonia data from High Sierra that we'll be able to compare to Chesapeake Biological Lab. We haven't been able to send those to NWQL for here now. And these are some of the older data that we have. They do pretty good as we're getting into different nitrogen and phosphorus speciation. You can see that there is difference between what CBL is doing and what NWQL is doing in the shallow and deep areas of the lake. So to continue on with the update of the lab comparison, like I said, we are starting to get those results in from NWQL and High Sierra. We got results back from Chesapeake in February for June, July, and September and October of last year. So they're still lagging a little bit. I don't think it's taking quite as long as NWQL was taking to get us results, but it's still a bit of an issue with getting them in a timely manner. Everything, this first step has been done. We're comparing those, looking at them. And then in the next couple of weeks, we'll start this phase 2, part 2, doing the matrix spikes and sending the lab comparison. We'll be getting water from the south to north flow at the breach, and then the north side of the breach as well. Go through and dilute those to specific quantities and then a specific percentage of salinity. Spike those so that we're looking to have the same target concentration in all of these samples that we're sending. So there will be a little bit of difference between spike volume, but we're hoping that we can see how kind of at what level those interferences are to our hypersaline water. And those will be sent to Sierra in Florida. So yeah, that's really what we're wanting to see. And then we'll go through, get those run up and get the report to y'all shortly, or as soon as we're timed with what we have. But that'll be hopefully beginning of summer. We'll have everything to be able to present. That's the question. Sir.
Yeah, and I guess I just want to highlight that this is a huge priority for us. We understand that this nutrient monitoring program relies on these analyses. So tackling this pretty hard. Hannah's done a really good job of designing this, serial dilution and spike recovery study. So we'll be doing that shortly and sending off to all these labs. And I was really encouraged with the limited nitrogen data we have to see how well our external Chesapeake Biological Lab total nitrogen and total dissolved nitrogen data compared to our USGS lab. But it's like all these other constituents that we kind of. So just want you to know this is a huge priority for us, and we realize the importance of it, and just trying to find, trying to work with what we have, which is these are really hard samples to analyze, and our lab is still really struggling to kind of help us out. So.
And as I've looked over these just really quickly in preparation to talk about, what I could see happening is sending our nitrogen to Chesapeake, our phosphorus and ammonia to High Sierra, for the time being, because it's the best we can maybe do right now.
And then you mentioned in one of your slides, +2 labs. What were the +2s?
So one of them is Dr. Leffinghouse in Florida. It's the University of Florida, I believe it is. And then if we can find another, just to kind of chatted with the state lab a little bit last year. That's not really a thing we want to get into. Yeah. Sorry. Yeah, sorry.
Yeah, it's not
She
only
sneaks off.
important for shrimp, but now brine flies too. I
Yes.
mean, we're
Yeah, right.
expanding into the brine fly realm as well. So,
Yeah, and just so like, and we are limited now, again, as far as paying our labs or our outside labs or anything like that. We have one person in our office that has a credit card that can be used to pay for that. There is those kind of.
Yeah.
Landscape.
Also.
all right.
Okay. Well, I don't have as much as usual to cover this, this meeting. The first thing I wanted to point out is the last of the pelagic experiment data has now been published. So the phytoplankton work, which was first that we started experimentally way back when, now is out in a formal paper as of last week.
Yay.
So that's done. Trying to get it past reviewers who said that you should be doing the experiment in 2-liter containers or 20-liter containers was the problem. You can't do factorial experiments in a laboratory with units that are that big. So they didn't like smaller units, standard units that other people use. But we have a reviewer that. So anyway, that now is out of the way. So we've got all the pelagic experiments now. All right, first thing to do is look at the phytoplankton. The red lines here are the 1994 to 2023 averages with standard errors around them. The blue line would be the 2024 data, and a yellow line would represent what we have for 2025. We only have 1 point, January, done for enumerating the phytoplankton in the pelagic area in the lake. We just got February and March last week or the week before. So those are being counted right now. You can see that over the period from 94 to 2023, the average is very different from what we've seen. And I assume it's going to be very 25. Looking at the abundance of phytoplankton in the pelagic here, you can see that the yellow line for 2025 is the amount of chlorophyll per liter. And this year, that abundance of phytoplankton in the pelagic part of the lake is way down, as Connor pointed out, compared to what the long-term average has been. And in terms of even what last year we saw. Last year we commented how low January was. We commented how low March was. But we had a spike at least in February last year. This year, all along, it's been low. Why is the important question? Because Thomas, as we know, this is what's driving the shrimp and the shrimp production in the lake. It can't be temperature, in my opinion, because if we look at the temperature lines here, they're not that different. The big thing that we're seeing is difference in salinity here. Low salinities lower salinities than what we've seen on average from 1994 to 2023. Now, I'm going to stick my neck out and give some hypotheses on what may be going on here, because I can't verify any of this without the nutrient data from the pelagic water column. And that would be nitrogen, and that should be the driving factor here. There's a couple of things that are going on that right now we don't know how to deal with. One is the berm that was put out. All of the dynamics of what was going on in the lake from what we had previously, what was going on in terms of changes in salinity and lake volume and things like that. So we've got the berm, and only a couple of years of data with that berm in place to see what might be going on. But we have lake levels that are going up. And as the lake level goes up, the nutrients in the water should be going down because they're being diluted. You got so much nitrogen out there, you got more lake volume, there's less per liter in the water. That's one thing that could be going on. Another thing that could be going on is changing the dynamics of the microbialites. And that is going to be changed in two ways. One is as the level goes up, since we were down so low with the high past, we now have surfaces of those microbialites of the actual. They're now being recolonized by the periphyton or the biofilm. So as these biological units, the biofilms, start growing, they're really going to be sucking up nutrients out of the water column. Nutrients that otherwise would be used by the phytoplankton. And this is going to be intensified not only by the water column coming up and covering the exposed hard surface and recolonized by the biofilms, also this decrease in salinity that we're seeing in the lake is actually beneficial to that biofilm growing from experiments we've done. You got two things going. More surface area, biofilm to grow on, salinity conditions for them to grow more and faster. Now, I can't prove either of those, any of those statements. I'm throwing those out as possible hypotheses. But what's going on here to the abundance of phytoplankton in the lake. And this change in abundance of the phytoplankton in the lake is not due to grazing. There are no grazers out there at this time. So this all has to be dealt with in terms of resources for the phytoplankton to grow.
Can I just add to one of your hypotheses, Gary, about the berm? I think this is actually really important to consider because in Hannah's kind of nutrient mass balance paper, there's an enormous amount of nitrogen and phosphorus coming from the North Arm. And when there's discussions about berm management, it's really centered on salinity, but I have really interested in how off that nutrient load, which is the biggest in the whole lake. And so, yeah, that's something that I was looking at in more detail in that in her work, but I do think that we need to maybe start talking about that a bit more.
And we do have some nitrogen cycling archaea in the North Arm. So they're definitely like processing various nitrogen species. We're not measuring the nitrogen or the nitrogen species. Are of nitrogen metabolizing Haloarchaea, yeah, who are in the North Arm. So that makes sense. What's that?
Nitrogen increases.
I'm not measuring nitrogen. I don't know. I depend on Christine for that.
Yeah.
We all do.
I know. We're really trying. Promise.
From the north arm flow, those values are typically 2 to 3 times what we see in the south arm. So I would say on average.
You don't have as many, algal species who are metabolizing it. Right.
I've been curious if it was the bacteria.
Yeah, there's a bunch of nitrogen guys. Yeah. Cool.
Well, I was concerned that if the deep brine layer was building in the lake again, we were getting deposition in the deep brine layer, but that's not the case. But we don't have the flow coming back into the lake from the North Arm, and that has always been a source of nitrogen.
But that's been the case for a few years now. This is a little bit of another oddity that we're
Well, we
seeing.
have 2 years where we've had this anomaly starting to build.
I think your hypothesis is as good as any.
I think that's why you lean more toward the microbialite
Mhm.
recolonization.
Flow from the North Arm into the South Arm, that would be creating a deep brine. And that would just be holding a lot of that nitrogen in that layer.
But ultimately, some of that can become available. And
Definitely, yeah.
Right, when
Well, this is
you
really
get equal
just-
again between the upper column and the deep and the bottom, then you get starting to circulate again.
So
You don't see the overall, like, total dissolved nitrogen increase that much when there's a deep brine layer compared to when there's not. It's not a huge difference between the overall.
But you're diluting it. That's what you have to take into account. You're not gonna see a big difference, but you're diluting that deep brine layer. And we picked it up in the early years of the project, which we published, and Dave Knapp's did as well. That there, you could see fluctuations in the upper water column with the appearance and disappearance of the deep brine layer. I think it's the microbialites. That's my working hypothesis right now.
I want to point out, sorry, Liv, I want to point out our student, Olivia Presson, back here, who's going to shyly speak away. She's comparing some data sets that she's done on recovering microbialites to stuff that we did in 2011 and 2016, those data sets. So she's an environmental science major, but she has also a data science minor. And so she's been doing this in her data science capstone, like taking what she's doing in the lab and comparing these data sets. So we may have some more information soon on what species are present, but you're giving us a really important point that maybe we should look for nitrogen processing organisms in those mats just to see who's using nitrogen and how.
Or fixing nitrogen.
Or fixing it, yeah, okay, good, thank you.
But say this, the point was raised that when the berm was built, the focus was totally. I think I made the point at some time when we started talking about the berm,
You did.
that there could be other consequences than just salinity that we needed to consider with that change. And I hate to say it's not, you know, it's the old saying, it's not nice to fool Mother Nature.
No, but I think it just points out with everything that we're seeing, how important that this nutrient cycling and these nutrient studies are. And I don't think we can keep our eye off that. We need to continue.
It's
to
much
focus
more
on-
dynamic than we thought it was.
Yeah.
Much more.
In your nutrients, trends, aren't they dropping?
Overall?
What I noticed.
It looked like it in
Yes.
your slides, yeah.
But again, that's the latest data that we have is from
Yes,
October. I would say when we were out there in November, I had to dilute every chlorophyll sample that we took because there was so much in here. And the water has just been continuously fermented.
But it still wasn't higher than a lot of other times in our past measures, yeah. Okay, the shrink numbers, I'm not going to say much about because Connor covered it already, but you can see that the cyst numbers came way down in January, February, March, which Connor pointed out, and the naupliae numbers are way up now compared to what is normal, the red line, for the duration of the studies we've been doing on the lake since 1994. Okay. We've been working on brine fly demography, survivorship, and proportion that are survived, larvae, and transitioning. Feeding them now on the biofilm itself, not on the constituent species of the biofilm, but on the biofilm raised in the lab by us at different salinities and temperatures. And this is ongoing work, and I don't want to stress too much about this right now. And this is this is for a range, this complete work here on different salinities is only at 20 degrees centigrade. And you can see that the brine flies are surviving better as the salinity goes up. And the transitioning gets better as the salinity goes up if they're fed the biofilm directly. They're doing better on the biofilm than they're doing on the constituent species that make up the biofilm. But this is ongoing right now. Now, back to here's nitrogen values for the pelagic. We've completed measuring all of decomposition of materials in the pelagic, in that water column, phytoplankton at different temperatures, different salinities, shrimp bodies at different temperatures and salinities, shrimp feces at different temperatures and salinities, and green feathers at different temperatures and salinities, thanks to Mike sending us a batch of green feathers. And you can see that the phytoplankton remaining, what proportion of the phytoplankton remaining declines with temperature, so they break down faster at higher temperatures, which is what you expect. Not much of an effect on shrimp bodies, a little effect of greater decomposition species, and green feathers. They're all significantly down, believe it or not, with temperature, but sometimes more than others. Some materials more than others. Salinity, we found that the decomposition was the greatest at lower salinities. Decomposition declined as salinity went up. Same thing for shrimp bodies. The feces actually broke down faster at higher salinities, and green feathers was relatively flat. And as I pointed out in the past, we've put all this data together into a model that builds into the shrimp and the phytoplankton side of the model in the pelagic zone that is looking at nutrient cycling, nitrogen in particular. Now, this is going to show you pilot work in the that you run into in studying decomposition in different temperature and salinity. Let's look at the microbialite, that biofilm decomposition. This old data here is what we've previously presented. I said I didn't like it because the decomposition was so low for the biofilm over time, very little decomposition effect of temperature and salinity. I said, this can't be the case. This is almost, oh, it's more than half of the decomposition of what you see in phytoplankton. So there's something wrong there. So we did some more pilot studies, and we found out the way we had killed the phytoplankton was to freeze it. And then you took the frozen, the dead phytoplankton, put it into the lake water and measured its disappearance over time, measured by disappearance of chlorophyll. So what we found was when we froze it following the same procedures that we used for the phytoplankton, it didn't die always. A lot of it died by freezing, but a lot of it still was alive. We put it back in the water and it just started growing again. That's why there's such little decomposition being measured. But this is the sort of headaches you run into in working with things that you haven't worked with in the past and trying to anticipate what you're doing. So what we did is we froze it for a longer period of time. The ideal thing would have been to run it through the autoclave to kill it, but if the autoclave, it breaks this material apart and it basically is decomposing by temperature, steam heat, rather than biologically. So we froze things longer, and if you look here for this, with that figure there, you can see that the decomposition goes down much more and becomes virtually very similar to what you see for phytoplankton, which makes more sense. And you can see there's a good effect of temperature and a good effect of salinity. So anyway, when you do that, we're starting to put together decomposition effects of the different components of the benthic community, and putting together that eventually we'll be able to parameterize a model subroutine that looks at the nitrogen cycling in the lake on the microbial-like structures. Larval frass is not completed yet. None of these are complete yet, but at least we have some results for all of them. But the larval frass is always the hardest to work on because it's so slow to decompose. It has the shrimp droppings, and you have to run those up to 2 to 3 months. Okay, we've also been doing nitrogen and phosphorus content of the pelagic zone structures, the different phytoplankton. We have the percent nitrogen, we have the percent phosphorus. For the brine flies, we have cysts, nautilus, juveniles, adults, and fecal pellets. We have nitrogen content and phosphorus content. We're doing more shrimp data here to get standard errors on this. These were too limited, the number of samples that we ran. And then we have green feathers for the nitrogen content, and we're running phosphorus content. We've got nitrogen content for the benthic zone. We like nitrogen content, larval, pupal, adult, and larval for the brine flies. And we've got that for nitrogen. We don't have phosphorus at all. That's being, will be run, and I don't think Leanne from my lab is online today. She's supposedly in a meeting all day today going over some of the methods to do phosphorus analysis that are quicker and cheaper to do than the ones that we were using over here for the pelagic zone. And then the thing that is sometimes the hardest to do and the funniest to talk about is to convert those nitrogen values into units that fit into the model and the units that are being produced, measured in the model. So you have to have the phytoplankton content per unit of chlorine. You have the cyst content, nitrogen per cyst, nitrogen phosphorus. Adults, well, we have adult equivalents, so we took shrimp bodies. We have a nitrogen content of shrimp bodies, nitrogen content of phosphorus content. We have fecal pellets, the shrimp poop, nitrogen content per pellet that they're dropping out. That was the hard one to measure. As you not, it's just not only have to know the nitrogen content of a bunch of the fecal pellets, you now have to know how many pellets you had there to begin with, and then divide that into the nitrogen. And then we had to convert nitrogen of feathers into per bird. And that actually was hard to come up with, nitrogen, the amount of weight of feathers on a bird. I found other breeds and got a weight to feather relation to other breeds, and we got that. Do you have feather content per breed?
No.
So I was on the web looking for these measurements, and I finally got someone, found something, and I went to go get it, and they tried to charge me to get into their database, like $65, and I said I can figure this out another way, so. Anyhow, then we got have the microbial biofilm nitrogen content per unit of chlorophyll. We have the nitrogen content for bodies of all the brine fly life stages, and we have that nitrogen content per unit of frass excretion, fecal pellets being produced.
Hey, Gary,
Yeah,
what is the variability on these measurements? Are they
that's a standard error. Oh, on these, well, I didn't carry it over to the per unit,
Okay.
but here's the variability of standard errors on the measurements.
Got it. Thank you.
They're pretty tight.
Yeah.
And the difficulty here measuring all of these things is salt. You got these things, and if you put them through the analyzer, it'll give you nitrogen as a percent nitrogen per weight, but you got to be sure there's no salt in that. It just has to be the body. There can be no salt on the body, so you have to wash it down and get it free of the salt before you can do the chemical analysis. But you don't want to use so much water that you know, the cells lyse on you from the material. Yeah. Okay, that's all I have to say. Any questions?
Gonna throw there's nitrogen and phosphorus values in tumbleweeds.
Pardon?
There's a bunch of tumbleweeds in there.
I know. One of the things in terms of decomposition was we were talking at first of going out to the store and buying some chicken and putting it into tubes and letting it rot in the lab. And we thought that might not be such a good idea. We could find decomposition rates of ducks in water in the literature and said that's probably good enough for that figure. People down the hall probably would object to rotting chicken meat. Anything else? Yeah, thanks.
All right, this should help transition a little bit with this Forestry Fire and State Lands is revising their comprehensive management plan, and Jeff's going to go over that, and the wildlife perspective, we're going to look at them there too. So,
Great. Yeah, I think we've all probably heard in other locations that we're working on updating the comprehensive management plan and mineral releasing plan for Great Salt Lake. Forestry is also doing this similar CMP formal update for Utah Lake at the same time. So I think looking around this room is a great example of the collaboration that we've seen on Great Salt Lake, and just all the different groups working on things and sharing information and trying to piece together this puzzle. And this was something I've tried to put together a year and a half ago or so, just all the different studies that are going on. I think that the two primary things that we're looking at are water resources is been working on Great Salt Lake Basin Integrated Plan. Forestry is now updating the comprehensive management plan, and both of those will be feeding into the commissioner's strategic plan for the lake. And then there's a whole host of happening that factor into these so that we can make good long-term decisions how to manage the lake itself. What the CMP is not, you know, there's a lot that's going on, and I think the important thing is that we do not want to duplicate or replicate work that others are doing. So what GSLEP is doing is fantastic. We in no way want to duplicate that. What we want to try to do is integrate that into, pull this puzzle together. How do all these things fit together? There's upstream water management that the Basin Integrated Plan and others are working on. State engineers working on a water distribution plan. Division of Water Quality is working on the water quality strategy. There's a lot of things that are going on right now, and so those are the kinds of things that we're trying to better understand and see how, you know, how we can help coordinate these things. So James plan, you know, here's what how they're going to be managing sovereign lands as defined by the meander line of Great Salt Lake. So what they're looking for are strategies and decision support tools that can help them kind of keep an eye on what's happening and then what to do going forward. And certainly there's a rule book in terms of what we can and can't do in a lake. So helping guide them. I just wanted to touch briefly on this. This is something that we're working on now. Is the state has this land use classification map that was last updated in 2013 when CMP was updated. And what this does is really helps forestry understand, gives them as well as potential applicants if who want to use the lake to what can they do and what can't they do. And so there's all these different classifications, class 5 and 6, looking at existing resource. And so you can see the purple and the blue on the east. Class 6 is usually done with WMAs. Class 5 has been, actually there's areas described in the statute where the state wildlife board wants to preserve for wildlife. Classes 1 and 2 are generally where there are existing leases and industrial activity on the lake or state park activity. And then class 3 is kind of a catch-all where the state is open, is open to consideration of any use. And I think what's important is that with the responsibilities of forestry fire state lands is they have to manage the lake for multiple use sustainable yield. Public trust doctrine certainly plays into it as well. And so the challenge is how do we all these different uses in a resource for. So there's a lot that goes into this, but this is one of the visions that we had for the CMP. I think we're all transitioning away from paper documents into more online references and tools. And so that's one thing that we're working on now is to try to, we'll still have to have a paper document, CMP, for the record. But a lot of the information, hopefully the most will be useful for managers, for stakeholders, will be available online. And so this is just one initial concept that we have before we even dove in, but just provide some situational awareness of where are we today in terms of water level, salinity. What does that mean in terms of, as this page is looking at salinity management, where are we? How does that represent in terms of the other? I try to have a heads up on what kinds of strategies, short term and longer term, references to the work of others, trends, etc. Really trying to make the information that's most helpful available, easy to find. And so the way we're working toward that is building a website for the CMP. This is actually live right now with the QR code there. There's a homepage, is just a description of what the CMP is, why we're doing this, and the FAQs, common questions that we've been hearing. And then right now, there's a more focus on the public participation portal. Last fall, we did a number of public meetings around the lake. I guess it wasn't unexpected, but we did not have a whole lot of people show up at those meetings. But via this, we had, and I think we still have, and provide comments. But we had over 300 people participate in the survey, which was fantastic. And so if you go to the website now under that public participation portal, you can see kind of a summary of what we heard. And it was, I think, very helpful. So as we're working on this, it's important for us to be aware of what conditions are today. because that influences the decisions we're making today, but also leads in terms of the trajectory of where we want to go in the coming months, in the coming years, et cetera. We want to try to reduce the amount of regret that we have as we look back and say, wow, I wish we'd done that. And so the two primary metrics that we've been looking at have been lake level and salinity. 10 years ago, it was mostly about lake level, and we're starting to see that salinity. The discussion today, I'm thinking, we're looking at nutrients. But we're just trying to, looking at all the different uses, how can we make this information easily accessible and look at the interrelationships between all of the different uses. So you can see these 6 different categories where things are kind of starting to come together. But we see in a lake level and salinity, and we are working on updating the lake level matrix. And also looking at the salinity matrix that the salinity advisory committee put together. And so, we're talking about, what should be the high point, what should be the low point, where are the break points that we want to have, different categories, thresholds for management. And there's a lot of good ideas in how we break that up. Also on salinity, I think just, the observed record, the red are just areas where we have no idea, except we can probably surmise that it's probably not good. If we go above 4212 or above 2295 in the south arm, or below 4188 and 50 for salinity, we haven't been in those ranges before, but based on the trend that we've seen, is that it's probably pretty bad. So those are just the kinds of things that we're working on. And then just thinking about tools. There are proactive things that we can do, coordination, communication, is a great example of that. Monitoring and planning, the work GSLEP's doing is a great part of that. Regulatory reviews, fix that, are part of it between, there's a number of agencies who have regulatory responsibilities with the resources on the lake. And so they have to review proposals, review conditions with the lake. Levers in the system. Now, obviously, inflows to the lake are potentially a lever. That's a big lift, but that's something that's being looked at separately. Water management within the lake, and then causeways and breaches that we have in the lake are potential tools for us. And as we heard this morning, is we have to be very careful and cognizant of potential ramifications or consequences of how we treat natural systems. I know as an engineer, we love to put things in boxes and like keep them in boxes, but I think, with natural systems, a resilient natural system depends on those pieces and those low points. It depends on that natural variability. And so how can we do that in a way where we don't? So just very briefly, our thoughts are, there's a lot of different people.
Jeff, can you go back to the last slide? Just point of clarification, I find that confusing, that the salinity should be flipped over up there, so it matches with the lake level.
Oh, yes.
And I was looking at the two greens, I said, boy, they hardly overlap at all, ideal and ideal. And then I said, oh, wait a second, that should be flipped the other way.
Yeah, oh, that's a great, I love that. Is that, those are to scale.
And they're linked.
But they are very much linked. Yeah. I love that. Thank you. So, and then I know one of the things that the Salinity Advisory Committee has been talking about is we identified a range of 120 to 160 as where we want to keep, where we'd like to see the salinity. And also recognizing that we need lower salinity for the cysts to hatch. And so what is that range? I don't think the committee's officially approved a range for the spring, but generally, some of the thresholds we talked about are 90 to 130, is that right?
Yeah.
So those are just, more variables for us to think about. So when we think about the people who are watching the lake, we want to engage people, we want people to be aware of what's happening and be connected to the lake as well. And so there's folks, I think the public, policymakers are often wondering, well, how is the lake? And so, we want to be able to provide information that's easier for them to understand rather than, the full matrix of things. When we talk to people, when they look at it, they just look at the green band down the middle and say, where are we in relation to that? They don't get into all the detailed columns that are in there, which are all very helpful. But for them, I'd say the majority of the population, they're just looking at where are we in the band. And so our thought is that there'd be a dashboard where we would have a basic lake level matrix, a basic salinity matrix, and then provide high-level strategies for the current paradigm. If the lake is low, you need more water, if the salinity is high, we might need to export salt to the North Arm. Some basic things like that allow people to understand where we are. But then as we start to, for people who are more intimately involved with the lake, there's a lot of 6 categories should correlate to those 6 circles that I had in the previous, but where people are wondering, well, what's the status of the different parts of it? And so our thought here is that within that, on that online tool, is that there would be a page that you can go to for each one of these. And so this is where we could dive into more details of this the lake level matrix and say, okay, well, for and pounded wetlands, here's the lake level matrix for those. For recreation or on the biology side. And the great news is that I think forestry and I think actually a lot of people work on what's on the hydromapper now, where that overall lake level matrix has been simplified into different parts of the system, so we can take a look at that. So each of these pages would have its own matrix for reference, the lake level and salinity, but then get into those, well, how do we manage each of these different resources? This is where we do want to link to what everybody else is doing. We don't want to replicate, rewrite what you all are doing. We want to be able to have a place where people can easily find what about brine shrimp? I don't want to rewrite anything. I know Wildlife Resources has a great website, so the intent is to be able to link to that. But we do want to be able to identify, well, what are some resource strategies based on lake level and salinity that especially foresters should be aware of. You guys are in the trenches dealing with this day to day, but for policymakers, decision makers, like your and we're ultimately should be thinking about. And then of course, forestry has to consider proposed uses. People come to them with applications with proposed uses. What does that mean? If somebody wants to do something along the lake shore or on the lake, how might that influence these different resources? So I think just very briefly, we're just looking at the biological status. Here's what's on the hydromapper now. Just for the biological components of the lake level matrix. So they've kind of consolidated things to kind of give you an idea of where things are at with each of these different parts of the ecological system. Same on the salinity matrix, where we can see where we stand there.
Is that you, Chris?
And then this is an example of what we're starting. This is totally water lake level. The salinity committee, Christine's working to try to get us to a point where we have the salinity that we can use an average salinity for the upper water column of the south arm. So we have a number that we can then compare to the salinity matrix and the resources. But then when we have the different web pages, and this is just for wetlands, is that we can get into fringe and high wetlands, low fringe, what are the trends, who's doing what is the desired outcome, vision for that, and then what are some management actions that we could be taking and strategies that we should be working toward. And then, guiding principles, dive into more and more detail. I'm never present. Okay, Lynn.
It says, thank you for all your work on behalf of Great Salt Lake. Big briny hugs. We hope I can maybe but anyway, so we'll go join friends on May 15th, 6:30 to 8:30 at Wasatch Community Gardens for the 23rd Doyle W. Stevens Research Program to learn and celebrate GSL research by university students. We go, and that's the lead in solidarity, but so I think okay.
All right. Thanks, Lynn. So, but this is where we'd love to get input. Again, like with GSLEP, you have a whole program already set up. And I guess what we'd love to be able to do is some links to what you're already doing so that a division like Forestry Parks and Lands can say, okay, how do we, we have to keep an eye on what's happening with brine trims and what you're doing to manage brine trim. How does that, how does that interface with what Vision Water Quality is doing on the water quality side, with what state engineer is doing on distribution, what forestry could be doing, etc. How do we together so we can just make sure that we're all going in the same direction. So where you all come in is, you guys are the experts, and we want to make sure that we're integrating the best information. And we want to, I think you want to try to understand better what you see as the management challenges and what strategies that you see that we can implement. And then we can start to look at how those might overlap or interconnect with what others are trying to do in the lake as well. So in terms of just on the timeline, we're in the throes of developing the plans right now. The goal is to have a draft CMP and releasing plans done this fall, in the October, November timeframe, and then that'll go out for official public comment. But here in the short term, I think the two big things that we're trying to make, what are they? And what's allowable, not allowable, potentially allowable, and where, and then also trying to, review and update the lake level matrix and the information that we have on all of the different resources. So there's a lot of great information in the current CMP, the 2013 CMP that we're going to roll into this. But some of it needs to be updated. And I think when I've looked at it, the things that need to be updated are because the science keeps improving, which is great. But when we only update a document every 10 years, things get out of date very quickly. And so that's one reason why we're looking at having a CMP that's going to probably be a lot shorter and more focused. And the online tool is where all of the details can be, so that forestry can update the tool. We're still working with the legal side of it. Where's that threshold of where we have to go through a whole public comment period, update something? But that's a way where we think we can maintain a CMP that provides the overall vision for the next 10 years, but then the flexibility to be able to adapt to as we learn. I mean, what's happened in the last 10 years in the lake is the change that we've seen is crazy. And what we've learned as a result is amazing too. And so how can we try to be flexible about that? So I think that's excellent. I guess that by virtue of that, I'm done.
Yeah.
Like I said.
That's the way Kyle
Any
cuts
questions?
you off. That's new management around here.
Good. I mean, it's, we've advanced a lot of our knowledge since the last iteration of this comprehensive management plan, and to go forward and hope to be more adaptable is a good way to do things. And I think we've learned a lot, or we're in the process of learning a lot that can feed into that. So.
Yeah, the number of studies that are happening right now that will be completed or plan to be completed in the next 6 months, amazing. And so that's where we're like, how do we write a plan that is going to be out of date before we even get to drafting the issue of draft or review? Because all the work that's going to be finished this summer. So that's where we're trying to. Yes, Laura.
I have a question that I think would be helpful for this group to weigh in on. At some point, and it doesn't sound like you're quite ready for it yet, but maybe, you have it up there with your matrix, but it only went to 4188. How the new one, what's an acceptable range? And I think contributions from this group would be helpful to consider how low they would like to go.
Right. 4188 is not acceptable.
No, it's not, but failing to look at what could happen as it goes even lower with your response.
Yeah, no, I completely agree, Laura. That's what we've been wrestling with. I think on the flip side, there's a concern that if we show a lower, that might indicate that it might be acceptable. And so we're trying to find that balance of, what do we show? And so right now, I think our thought is, we want to indicate that below 41, we haven't seen below 4188 before. And we know that everything at 4188 was, most everything was in trouble. And so we can pretty safely assume that if we go below 4188, everything works. And so it's
Putting a bottom on it.
that's so. How do we communicate with people? And I guess what is helpful for many is, I think, I think we do want to contemplate what does happen. We do where are the microbials completely exposed? And so where's that threshold? Where is the North Arm disconnect from Carrington Bay, and then Carrington Bay disconnect from the other bay? I think those are all important things that we can address. But I think the lake level matrix has been such a great graphics tool, to communicate where the lake is, and I just make sure we communicate the right things. Yeah.
4188, you wipe out the biology essentially after that point there. Once you're below that, read about the Salton Sea, what's going on now, where the health issues now are filling the news pages. So I think that's where it goes. It shifts from the biology of the lake to the surrounding health.
Yeah, I think to show how, when it starts to affect human health and economy compared to just industry on the lake and biology in the lake. You've got to show it empty before people are going to understand what will happen.
Just put a international sign for toxicity below that level. I mean, if you have to make the but I don't know if you could still pull up those slides and go back a couple things a couple of thoughts. I think one of the versions we have 4177. At Island, that divides the other bay from Carrington Bay. I mean, at that point, all the inflows only in Gilder Bay and Carrington Bay and North Arm are disconnected from surface water.
That's the zombie apocalypse, basically.
But we don't want to communicate it like that might be a solution.
Or at
So,
least, is zombie apocalypse below Mad Max? Is Mad Max prior to that, or how does that work?
Actually, I think it would be, Mad Max would be above that.
So I had a couple of questions here, Jeff, on sort of management of water. When you talk about storage, diversion, conveyance, is that what you mean within the lake system itself? I mean, for example, in my mind, if the lake levels go down low, we shut off the north arm, which, by law, I can't remember exactly what level that was, 4190 or 91 or 99. I can't remember. But I mean, there's a level where we shut off the north arm. At that point in time, low north arm is going to evaporate. We hope to maintain enough inflows into the south arm. But occasionally we'll probably at that time we'll be exporting brine to the north, with that exporting salt, reducing that salinity in the south arm. How do we get that salt back when we need it into the south arm, which would be an active management? And I'm wondering, is part of what you have in there, like diversions, would that be part of that sort of management, or would that be something different?
That would, I think that would be part of it, is, if we were in that situation where the north arm was disconnected and we needed more salt, then, one of the options that the Salinity Committee talked about is a pump station to pump north arm water water and salt primarily to get some salt back to the south arm.
Yeah, rinsing of the ponds, I think, was another one. Yeah. And the other had is inflows to been talking about the Newfoundland Basin and the water that evaporates there every year and brings that back into the lake. Would that fall under inflows? Yeah. Okay.
Yep. I think those are all, I'm trying to think if there are any others. I think those are the primary. You've got the major river basins on the east side. They have Newfoundland Basin on the west side. And how can we manage those? And so, I think, as I understand it, there's definitely some complications. Well, I guess there's complications with all getting you close to the lake. But in Newfoundland Basin, there's questions on who owns the minerals and Newfoundland Basin. So there's nothing that's really very easy to identify these things. But I think what we want to do is we want to try to identify, okay, here are some of the potential tools, and that we may need to consider if conditions get to that point.
I mean, personally, I think we should have their own nutrients. The real proponents of continuing to study that, USGS work with nutrient cycling and continues to show how important it is. And when we were working with Division of Water Quality, came up with some interesting solutions. I think you came up with one, Jeff, where we rerouted the effluent of the PLTW back to the hypersaline portion of the lake and bring those nutrients in. Another one was, I think, when we were working on the nutrient criteria, we developed these criteria as a combination of these nutrient criteria and ecological responses in order to try and avoid too many false positives and, for treatment of the water. And we need to bring nutrients down to the lake. We put the lake on the back burner a little bit with DWQ when it comes to nutrients, but I just think it's so important to continue to understand that nutrients flux.
And have to add a column right there now.
Help remember to put on that.
What?
Lynn's still around. She got her hands up.
Oh, hi, Lynn.
There. Sorry, I'm having audio difficulties, so I hope you can hear me. And Jeff, I didn't mean to break your. Oh, sorry. When you were presenting. I just want to confirm. Oh, sorry. I just wanted to confirm that in the CMP, the focus is still only to the meander line as far as management decisions. Is that correct?
Correct. That's correct. So yeah, the CMP is looking at what's happening. And I think that's where, a lot of, frankly, most of the comments that we received in, during our public, communications last fall, almost by far the most frequent question we got is, how are we going to get more water to the lake? And so that's where I was told Millennium in Colorado. And then that's where the other efforts that the state's working on come in, is that those they need to, we need to understand what are the challenges, the consequences of, within the watershed and getting water to the lake. What are the consequences and challenges at the lake if we do or don't get water to the lake? Because there is a cost associated on both sides. And so we need to, I think right now, I think there's a lot of feelings as to what we think those are, but we don't really have the number. And so I think that's the intent of these parallel efforts, is to try to characterize those and get information out so people understand what we're working.
All right, well, thanks, Jeff, and
Thank you.
I think one of your last slides that had the fringe and impounded wetlands, I don't know if that was on purpose, that transition and segues into our last presentations. And Lauren and Brian both said they would speed things up, and we're going to try to finish and then have lunch. So
Don't worry, I'm staring at the blue the entire time, so I'll go fast.
Hold on. I gotta get Brian's presentation over here.
Is it dead?
I have the clicker. Because the state upset. Some people.
In the internet.
All right, so for those that haven't heard me speak before, my name is Lauren Head, and I'm a PhD candidate under the advisement of Mike Tolliver at Utah State University. My education is helping to develop a water biodynamics model for impounded and possibly managed or fringe sheet flow. There's a lot of different names, wetlands around Great Salt Lake. So my project primarily focuses on that we are hoping more as well. To keep it brief, my project updates are generally just going to be, we're heading out into the field tomorrow to wrap up our last session of food availability data collection, weather permitting, and we'll be done with that study at the end of April. Also be discussing sample processing update, as that's kind of the crux of this whole deal. And then as well as presenting on some preliminary spatial data and some preliminary water bird data that I've been working on for my past year and my first year of the data. So for those that haven't heard it before, the project objectives are to conduct an observational study that evaluates technical availability in open water wetland habitats during both fall and summer. So we kind of are trying to measure what resources are out there in terms of macroinvertebrates, seeds, and submerged aquatic vegetation, kind of throughout these peak periods of resource density. So for us, that's April, August, and November. That are available in the open water wetlands. with what we know about water bird population dynamics. We take our own estimates in the form of point counts, and then we're basically able to use published estimates of thermoregulatory needs for waterfowl and shorebirds. And we can use those published thermoregulatory needs to determine how many calories a bird needs each day. And then we can basically compare supply versus demand. So we take how many birds we have versus how much food is available in order to model, how resources are being depleted and whether or not there's enough energy available in the system to support the birds that we have passing through here every year. So the goal is to do kind of a standard model that's used traditionally by a lot of joint ventures, so that we can compare previous joint venture models for Great Salt Lake, and then also trying to develop a more predictive data set that can allow us to sort of evaluate how different water resource scenarios may impact our wetlands. So our observation takes place at 6 different sites across the wetlands. So we have areas, those are going to be in kind of salmon color, and then we have bare that is in can. So these are going to be impounded units, and then we have Willardsburg and Barnacle Bay, which are our 2 representative sheet flow wetlands. And it's important to remember that these areas, this is kind of an example of what our survey areas look like. So you see up on the top, we have the managed areas. These are going to be kind of split out into ponds that are managed very aggressively for submerged aquatic vegetation for waterfowl, as well as for water depth. So we're able to actually manipulate using using like dikes to draw that level up and down based on the bird needs. Whereas our passively managed sheet flow wetlands along the bottom, these are going to be much more subject to inflows that we've been talking about based on runoff and things like that. So they're going to be more variable in terms of food resource availability, but they also have greater heterogeneity of habitats. Timing, as discussed, is in April, August, and November for 2 years. Another thing we try and control for hunting pressure. So you'll see that red area up at the top is a hunted area, and then that blue area up north of that is our rest area. We do this to control for hunting pressure during the fall when we're assessing bird densities, because birds typically are congregating in those rest areas since it's not really safe for them to be in the hunted areas. So as far as our sample processing update goes, those that have been here in the past know that this is a bear of a process. We are currently over halfway with our first year of data, processing, which feels really good for me. So we have a total of about 1440 samples for year 1, and we're a little over halfway through that. As of right now, I'm projecting that we should be finished with data by August of this year. And then actively seeking grant opportunities to try and expand our workforce so that we can process more samples faster, because we know you guys are eagerly waiting for this biomass data, and we want to get it to you as efficiently as possible. We have received a USU grant to hire an additional part-time technician already for fiscal year 26, and we're hoping some more grants will come through so that we can expand our staff even more than that. But I've been very fortunate to have some really hardworking technicians that have continued to return and count bugs for the past year and a half, and I promise, counting as fast as they can. So yeah, in terms of spatial data, this is the part that I'm a little bit excited about. So I've been showing you guys these box plots over the past few, basically since I started the project, that have kind of showed us how water depth and submerged aquatic vegetation are distributed, just kind of on a graphical scale. I managed to go through and kind of with our spatially. So last time we kind of established that in our managed areas, we're seeing this effect of hunting pressure manifesting itself in our hunted areas. So we're seeing greater quantities of submerged aquatic vegetation being retained in our hunted areas over the course of the hunting season. Now, whether this is a result of these areas being a little bit larger than some of our rest areas, whether it has to do with the amount of vegetation that they're less to begin with, those relationships haven't quite been established yet. But it's really interesting to see how significant some of these trends are. Because in certain areas, we're seeing about 45% more SAD being retained in the hunted areas than we are in the rest areas, which is suggesting that these birds might be depleting these areas really fast. So, but what are our unmanaged areas? So our unmanaged areas are a lot bigger. They're a lot more heterogeneous.
So we weren't able to model them the same way that we modeled them in the generalized linear mix model. So I decided to kind of tackle that a little bit from a spatial perspective. So we did this in GIS, and basically I took my points, measurements of depth and submerged aquatic vegetation from August of this past year, and used basically the distribution of those data points and those values to kind of predict where these where depth thresholds might be and where submerged aquatic vegetation might be based on what we collected in the field in past August. And so I'll kind of get into a little bit of what this looks like. So this is going to be just focusing on Willard Spur. I need to do a little more work in Bear River, so don't pay too much attention to that. But this is generally what we're sort of looking at based on my 40 points that are in Willard Spur. So this is overlaid. I was able to obtain surface water polygons from the Intermountain West Joint Venture GSLEP tool. So this is what we predict surface water actually look like in August of 2024. So areas that are in the polygon flooded, and then my data is able to come this. Now, this is based off of 40 points. This isn't nearly as comprehensive as something like LiDAR, and our hope is to eventually expand this and incorporate that LiDAR into some of these estimates. But a lot of the LiDAR that we had was taken on land and doesn't do a great job of penetrating water. So this is one of the ways that I'm trying to tackle that. So as you can see, we're pretty shallow in the spur in August, and so this had some implications for submerged aquatic vegetation. So see, a lot of our area was below that kind of 10 centimeter threshold, and 20 centimeter threshold. With only a little bit of area kind of being through that 20 to 50 centimeter range. And I talk about the 20 to 50 centimeter range because when we're thinking about this in the context of birds, right? Our waterfowl and shorebirds are not really going to be able to access water below certain depth thresholds. So for ducks, for dabblers specifically, that's going to be below about 50 centimeters. And for shorebirds, that's going to be, depending on the species, below about 30 centimeters. So, and then divers can, more than over that 25 meters threshold. But distributed, you can kind of see how those shallow areas may be influencing some of that. And I know that we had some kind of, some interesting situations with timing water delivery in that over the past summer. So it's interesting to see how that depth may correlate to our submerged aquatic vegetation densities in this area. So yeah, and just to orient you on this graph here, this is a proportion. So this is, think of 0 as 0%, and then 1 as like 100% vegetation. So there's some patchiness within that, and this isn't perfect because this is all interpolated based off of 40 points. But it's worth noting that these are kind of, we've systematically designed our transects so that we're catching that heterogeneity. So this should theoretically be capturing some of those relationships and tracks at least with what I observed in the field. So now we get into Farmington Bay, which had a little bit of a better. We can see that we maintained depths a little bit better. So we have a lot more of that kind of darker blue, but not too dark, where we have, that range between about 20 and 50 centimeters, give or take. And so, yeah, this is really interesting when we look at our submerged aquatic vegetation. So we can see that right in those areas of that 20 to 60 centimeters in depth, we're seeing these really dense flushes of vegetation that are occurring in August. And that's very much on track with what we've been observing when we're out there. And so I think it's going to be really interesting as we continue to develop these models to see whether or not we can actually nail down these formalized relationships between depth and submerged aquatic vegetation. We know there's probably other things going on in terms of water quality, and we've got USGS that's helping us kind of work on that side of the puzzle. So yeah, so now I'll kind of get into my work on evaluating relation metrics. And this is going to be kind of for densities, for behavior, and water depth. And collect our own data in the form of point counts. And we basically do monthly distance sampling during the summer and fall. And we're emphasizing our areas that we're surveying for food availability, as well as other open water habitats around the areas. So we go out, we calculate distance from the observer distance from the observer using range finding binoculars, and then we're able to use that to project these detection functions essentially to determine approximately what our density of birds are. So obviously, this is not going to be as comprehensive of a data set as like the census surveys that the division does, but it's something to give us some metric of, you know, how birds are doing and where birds are spending their time. So what I'm going to be discussing today is going to be kind of aggregates. So this is going to be kind of total sums between summer and fall. And so I'll just get right into it. This is going to be for dowlers. So I'll kind of orient you a little bit, but my species are listed here. So this is what species were kind of incorporated into this detection model. We do this in fall. I split it in fall and summer. So fall, I think September to November, December, and then summer was from April to August. And so then I've got my sites listed across the bottom, and then just keep an eye on these this y-axis here because this will change as I go through these slides. So these are not going to be necessarily extrapolate. This is just density estimates, and so we're looking at kind of overall trends. But I think some interesting things that emerge when we look at the dabbling densities is that we're seeing really high quantities of dabblers in these areas that have larger proportions of rest area or like intermediate pressures, right? So we've got Bear River, which is very largely rest, and then far outside of Farmington Bay, which is the loud intake, we don't necessarily see that. It's also important to think about, while this is my first year data, so this doesn't perfectly line up with that data that we discussed in with the spatial data that I showed you earlier. Farmington Bay is emerging as a really important site for submerged aquatic vegetation. So that could be another reason why we're seeing a lot of birds come there. So yeah, and then in the summer, we're seeing kind of trends that we might expect, where we're not having a ton of birds that are hanging around. And remember that our dabblers are preferring those depths about 50 centimeters or under. So they're also prioritizing areas based on what's available to them and water depth. I modeled teal separately because teal are a little bit different and are known to kind of spend their time in the summers on Great Salt Lake. So anything you see in blue is probably going to be mostly cinnamon teal or green teal and always around. But yeah, so we can see that Bear River is once again emerging as a pretty important site for these guys. And fall as well, you know, Farmington Bay. So yeah, these guys prefer to forage a bit shallower. And yeah, you know, we're seeing they're spending more time in the wetlands during the summer. And then when we get into divers, these are the species that we model for divers. We're seeing a really interesting trend emerge, at least I feel like. So remember that some of our point counts are going to be more skewed towards our sites that we're assessing availability, right? So when we look at our site in Farmington Bay, these are the two impoundments that we're sampling for availability. And so a lot of our estimates from those, a lot of our density estimates from those are on deeper waters, and we're seeing that across all of our sites. Farmington Bay is our site that has the deepest impoundments, and so we're seeing higher quantities of divers in those impoundments, which I think is really interesting. So in summary, you know, these are general density estimates. We don't have to use tube every single year. So I think, you know, future goals with this work is to kind of, you know, contextualizing these and these estimates in the context of other data sets. We also need to really nail down what is total available habitat for these individuals when we're extrapolating abundance. Because if we just extrapolate out to the entire size of the WMA, that's not necessarily representing the amount of habitat that's there. So I think leveraging tools like the wetland evaluation tool, as well as some of these other, you know, habitat resources we have access to, like National Wetland Inventory, and maybe updating those would be really great. Yeah. Things that we can consider leveraging. We also need to be considering hunting pressure when we're modeling these relationships, because it does appear to be playing some kind of role in the way these birds behave on these wetlands. And we do want to kind of tackle this piece of kind of nocturnal foraging. I'll let Brian touch a little bit more on that. And yeah, for at least a few species, I was trying to check and contextualize my data in the context of some of the data we already have. And for it seems like my summer trends are generally aligning with the fiber water bird survey. So yeah, future directions, we're trying to nail down how we want to use these GIS bathymetry resources. We have really good bathymetry data for Bear River migratory bird refuge we learned this week. We also have LiDAR data that we can leverage that's going to be great for like super shallowly inundated areas. But the biggest thing that we've got to nail down is kind of how to get at these, these inundated sites that weren't covered in the 2016 LiDAR. And MyData may help with that. I know USGS has published a data set that kind of combines the basking and the LiDAR imagery to sort of try and get at that. So we may be using a combination of those resources in order to actually get at what's going on in terms of like how depth is distributed and stuff. We can then basically bin open water into different depth thresholds, and then we can assess how many calories are actually available to these different foraging guilds and what habitat is available. Pairing these with driver food availability as well as biomass estimates so that we can actually figure out how many calories are available to each species of birds on the landscape. And then we'll hopefully build this into a treatment model for water valve, which is kind of traditional bioenergetics model. And then my hope is to at least establish the framework for either an agent-based or Bayesian hierarchical framework that allows us to incorporate both risk and depth into the way that we calculate bioenergetics. Because I think those are emerging, at least on the Great Salt Lake ecosystems, as two really important factors that we need to be considering when we think about how we'll do this. So yeah, with that, I'll take any questions.
All right. Thanks, Lauren. Awesome. All right. Well, we'll finish up the last presentation. I'm going to blame all of this go down on Kyle because he's taking over. So
You start running this one.
I want to introduce Brian to everyone. He is a master's student who started in January. He's already written his proposal and gotten it through his committee, and that the proposal basically details the steps, methods he's going to take to answer these questions. I'm also need to report that Brian has impressed a number of people here. Ryan and I were in my office yesterday, and we were talking to John Left about some of our methods that we were thinking. And John said, you know, I have every confidence in him. And I said, wow, John, that really makes me feel good that you have that much confidence in me. And then John said, I wasn't talking to you, I was talking about Brian.
exactly.
All right, everyone, have Brian Krugzak, Utah State University. My project is developing bioenergetics model for American absinthe and black neck stilts with great solid levels. So kind of some background why we chose to do absinthe and stilts. They're both very charismatic species, public related species as well. They both overlap in a lot of separate things. So, you know, they both arrive into part of the Great Salt Lake similar times. Both have very similar foraging methods, both have very similar diets. So that's kind of why I chose to study these two species. So with that, that kind of leads to our project objectives to build a bioenergetics model. So what we have to do for this is quantify the density of invertebrate prey, quantify the amount of foraging habitat in both these species, and then we're going to estimate the densities of absinthe and stilts across the different habitats on Great Salt Lake throughout the same period. And that's going to be through impoundments, sheet flow vectors, and flies as well. And some other things to know about the bioenergetics models for these guys. So what we have to do after we quantify invertebrate prey, we will then go through it. Birds that eat in one day, and that'll equal one bird day. And once we have that information, we can then determine from the density estimates throughout the entire sampling period, the total bird days. And from that, we can then identify the millions of kilocalories that these populations need to be sustained at the Great Salt Lake. And then with that, we can put this into the bioenergetic model and then determine the carrying capacity throughout the study period. So this leads to our site selections. We have 3 impoundment sites, 2 sheet flow sites, 20 flies. So as far north is public shooting grounds that we made, as far south is Farmington Bay. And these 20 flies are going to be dispersed throughout, ideally around 5 by each of these sites. So like I mentioned earlier, both these species have very similar diets and they forage in similar ways. They birds out of the water column, birds out of the air, and then they will also stir up the top 2 layers of sediment if it's penetrable. So because of that, we needed to collect 3 different samples to quantify the energy supply for these species. So that leads us to how we're going to do that is with the stovepipe sampler and then the sweep netting as well. So with the stovepipe sampler, this will let us get 2 out of the 3. It'll isolate the water column and then the top few layers of sediment. Essentially, what a stovepipe sampler is a 5-gallon bucket with the bottom removed. You can put it into the water, collect all the water out of there, seed it, collect the macroinvertebrates, and then there's also the organic material in that as well. And then it also isolates the top 2 layers of sediment to collect into bags. And with the sweep netting, this will let us quantify the near surface brine flight density. So what we're going to do, where we take a stovepipe sampler, we're also going to do 1 sweep net there, and then 2 others on the transect running through where we stovepipe sample. And so with this, we are going to, so one's going to be collected directly from an actively foraging abscent or silt. 2 additional controls. So for example, within the impounded areas that we're sampling, we're going to do within the impoundment control. And this essentially is staying in the same impoundment. We're going to drive 1 kilometer down from where we sampled from an actively foraging bird. And then we're going to go to where there's no birds, take a sample in open water. And then we're also going to do an adjacent impoundment control. This is going to be in a different impoundment, but try and find similar habitat. So, you know, if it's 5 frac running stand, we might do that. It's open water, we go in water, go out and take a control sample there as well. So when we get this information, this will help us quantify the energy supply in the different habitats. So with this, we're going to have to take our samples and identify the macroinvertebrate status at the family level. If we have seeds, we're going to identify that down to the genus level. And then we're going to have to sort through these samples, weigh each sample to get the weight. After we have we can then determine the energy. And with this, we can combine this and use the densities and prey availability to determine the total available energy at each habitat type that we're sampling. So then this leads to how are we going to quantify energy demand. So for this, Lauren kind of touched on it earlier, we're doing point counts. It incorporates distance sampling. So essentially we're going out with binoculars, with range finders, and counting all the birds we can see and getting the distances from where we're conducting the point counts. So for the impoundment habitats, this is going to occur at intersections of dams, and then applies the sheet flow wetlands. This will occur at transects around the habitat. And I'll kind of break this down real quick. So transects. So this is representative of like a flyer sheet flow. What we would do is we would go get a transect on the edge of the habitat and then select a random point. And then you go out, count as many birds as you can in 45-degree wedges. And then for the impoundment, kind of how I said earlier, this is at the intersections, but not exactly. 200 the intersection, just so that we're not scaring out birds up to 600 meters away. That's about the maximum distance. Some conditions for the binoculars to see. And then very similar process going out in 45-degree wedges, counting as many birds as we can. And so what we're going to do when we do this is record species, distance to the bird, and then the angle relative to the transect. It's kind of a 45-degree wedge aspect I was talking about. And then we're going to plug all this information into the arc package distance on this list, model protection functions, and then determine asset density estimates per kilometer squared. And then after we have all this information, you know, we've determined food per kilometer squared of foraging habitat. We're going to then figure out, because foraging habitats for assets usually consist of about 10 centimeters or less. So knowing that, we're going to use LiDAR. So this is kind of the LiDAR data from the urban bird refuge that we were talking about earlier. We can use the food per kilometer. The kilometer foraging habitat, and this will give us the total food availability, also known as the energy supply of these different habitats. And then behavioral observations are another important part of this project. So what we're going to go out and do is record the proportion of time of different foraging behaviors for both absent and silt adults and chicks. And this is going to be at different water depths. We're also going to incorporate nocturnal observations. And employ a night vision binocular to record chick foraging without disturbance. Kind of the thought process behind that is that there's various studies out there that show that nocturnal foraging and the important foraging behavior for these birds, specifically the rabbits. There's been studies that show that under moonlight they will forage more, and then later in later in the year towards migration they'll forage. And so the implications for man, why is all this important? So essentially, what this bio, we hope it'll show us there's a plethora of food for all these birds, and that they're, there's no problem while they're here the entire time. However, should there be any sort of bottleneck where they're not getting enough food, a bioenergetic model would highlight that. And this can be very important for managers to use that information to adjust and try and fix that. So, and from that as well, the bioenergetic model would be able to show differences in different habitats as well, or different times. So in conclusion, I kind of want to highlight the project objectives again, what we're doing. We are building a bioenergetic model that's going to quantify energy supply to different habitats. We're going to quantify the energy demand of birds, and then try and figure out the foraging habitat to build a bioenergetic model. And then this bioenergetic model, like I said, hopefully shows that there's a plethora of food throughout the year. But if not, this would be able to show any bottlenecks in any different habitat types or every different times of the year. And from that, I want to acknowledge all of the Division of Water, working for Fish and Wildlife, Delta Waterfall, Utah Wetlands Foundation, and of course, Utah State University. And from that, I also want to thank you all for listening and open it up to questions.
Any questions? Yes.
Both of guys, you quantify a number of bugs there, right? But not all of them can be eaten.
Correct.
How do you figure out the proportion that can be captured versus that number that are not really available? And of course, habitat would make a difference in that too.
Yeah, so habitat makes a difference, and then it's also just kind of looking at like dietary studies and then how that feeds the bird. So that you can figure out, that's kind of going into that diffuse days piece where it's like we figure out how many calories the bird can convey, and then we can sort of, I guess, use that to figure out like approximately, because we can basically take the caloric value of the bug, because we have the caloric data. We can use that to figure out how many bugs the bird is. And we can also, a lot of these dietary studies will kind of tell us what proportions of each of those bugs they're eating. So we have approximate proportions of how you can that.
But in a given square meter or whatever, they're feeding there. Now, some are going to escape.
Yeah.
How do you know what the number is that escapes? Some of them, the bird may quit at some point because there just aren't enough there any longer. How do you take that into account?
Yeah, no, so that was part of why I chose to swing netting. So, there's different like emergent traps, but that would show density, right? That would be what they can forage. So kind of the thought process behind the sweep netting portion of this is that as you go out, when you try to sweep them, some of them are trying to escape as well. So it's not perfect, but
to start.
Yeah.
Future research.
Yeah.
I have maybe a dumb question because I don't know much about birds, but the nocturnal foraging, is that also related to air temperature? Like, do they tend to do it when it's really hot outside? Or is that not related at all?
I don't know the answer to that question.
I know in waterfowl it can be dependent. I've seen some studies that have shown that it can be in certain circumstances temperature dependent. I don't know how it translates to habitats and still. I know there's both.
Okay.
It would largely be predation driven, predators. Being a small shorebird on the water, you're more likely to be eaten by something during the day.
Cool, thank you. That's helpful.
Awesome. Thanks, Brian. All right. Well, we're going to conclude. The only thing that I wanted to mention is the next couple of tag meetings are going to be scheduled for December 3rd, if that is with everybody.
Who were the two?
August 20th and December 3rd. They're both Wednesdays. Hopefully that works.
It'll work.
Okay. All right, well, we'll just call it good and go get